Chemistry 1112 students. This is Dr. Jingbo Louise Liu, your instructor for this Chemistry 2 during the summer 2. Our lab will be completely virtual. So today I will discuss very briefly about the experiment number 1, which is related to the nanoscience and chemistry. The objective for this lab lies in 3 key points. First of all, we are going to discuss about the basics related to the small world. You will learn and understand the history of nanoscience and technology. And then you are going to understand the importance of nanoscience and technology in our daily life. So students will also understand the application of different types of nanomaterials. Followed by, we are going to show you fundamentals about nanosynthesis and then some fundamental information related to the nano characterizations. The synthesis method essentially can be distinguished into 2 types. One we call the bottom-up synthesis. Bottom-up synthesis refers to you started from small, from atomic or molecule level to prepare the nanomaterials based on your end application. About your top-down synthesis is related to removal or reconstruction of your existing macro-scale materials by different approaches into smaller sized materials. The very last point is about characterization. So in order to understand the microstructure of your nanomaterials, we are going to use spectroscopic method to do some bond variation, and also we are going to learn electron microscopic method to characterize the morphology, the elemental composition, and the in-depth fine structure of nanomaterials. The very last method is X-ray diffraction. So you want to determine the phase, the crystallinity of your nanomaterials. So this course is based on the nanoscience and nanotechnology, and this lab is a dry lab. So you are encouraged to explore the small world, nanoscience and nanochemistry. There are 2 textbooks I'm recommending for you. The first one is called Nanoscale Science and Technology. So this book is available from our bookstore. The second, electronically and physically. You can find the physical book and also electronic book from our bookstore. The second one is called Functional and Smart Materials. This book, I believe I physically purchased a hard copy placed in the university, so you can use them. And also I recommended several different websites for you to understand, to explore the small world. So the first one is related, the first group is related to the government website. You can go to nano.gov. You also can go to different national labs such as Argonne National Lab, such PNNL National Lab, and also you can go to National Science Foundation to learn about the different nanomaterials. And also you have OSTI.gov for you to study, to explore. And also have several websites related to the peer-reviewed journals. So one of them is my favorite, is called Advanced Materials. Second one is Energy and Environmental Sciences. The third one is actually publishing companies, ACS Publishing. The first Advanced Materials, this journal is published by Valley. The second one is published by Royal Society of Chemistry Publication Company. And also you have ACS Publishing. Particularly I choose 2 different journals. One of them is called ACS Nano, the second one called Nano Letters. You can apply this different website. You can explore, to study more, to read other people's research discovery. Briefly about nanotechnology. So you need to know nanoscience and technology is a multidisciplinary field. This term is used to cover design, construction, and utilization of functional structures. At least one dimension is in the nano size. Nanotechnology is critical because this technology is going to provide understanding and control of matters in at least one dimension within the 100 to 1 nanometers. Nanomaterials, they have different applications, so particularly you can use them in the, say, energy field, in the biological field, in medical field, etc., etc. And then nanoscience also provide the different classification of nanostructures. Generally speaking, you have three-dimensional nanomaterials, two-dimensional nanomaterials, and one-dimensional nanomaterials. Regarding the fabrications, I summarized by two different types. One is called top-down, another one bottom-up. Top-down is related to the removal or reformation of atoms to create the desired structure. For example, you can use ball milling to produce nanomaterials. Another very commonly used top-down method is called the lithography process. So you also can produce different structured nanomaterials. You can also use machining, such as focused ion beam, to build different nanostructures. Another one is called bottom-up. The bottom-up process encompasses the chemical synthesis or controlled deposition and materials growth. So this bottom-up usually is from atom to atom to construct a desired structure based on your end application, such as you can have vapor deposition, physical vapor deposition, chemical vapor deposition, and also you can produce different semiconductors using molecular beam epitaxy. Another two methods, this colloidal method, and one of them sol gel method is my favorite. So I will choose this sol gel method to show you the different applications and different types of materials you can produce. Sol gel method is a chemical method. Sol gel method is chemical synthesis. So you start from metal alkoxide, go through hydrolysis and polymerization to produce a sol. From this sol, you can eventually produce hexogel films, and you produce different films with different thickness. You can also extract the solvent to produce aerogel. You can eventually produce dense ceramics, or you can even produce different sized nanoparticles. Also, if you use a high temperature, you can produce ceramic fibers. There are several different methods such as ball milling, lithography, and focused ion beam, focused ion beam, also called FIB. I will leave it for everybody to study by yourself. And then I'm going to move on all the way to the colloidal synthesis. Regarding the colloidal synthesis, I want to mention there are several different types of colloids. First one we call the aerosol, liquid dispersed in gas. Second one also called aerosol, solid dispersed in your gas. And you also have foam, solid foam, gas dispersed in liquid or solid. And you have emulsion, liquid dispersed in liquid. Solid emulsion, liquid dispersed in solid. You can also have a sol, such as what I did for my nanometals. You can have a solid dispersed in liquid. The solid sol can be solid dispersed in solid. So this is the colloidal method. This method is strongly involved in the sol gel method. A couple minutes ago, I gave you a very brief overview about sol gel method. There are some key points which you need to understand. There is something called this sol precursor dispersed in your solvent. This precursor is going to be subjected to the hydrolysis and the polycondensation reaction. Therefore, you are going to form a backbone involved in inorganic lattice. So remember, this bonding are very strong, meaning the substances eventually are going to be produced have very strong chemical bonds, meaning the materials will be mechanically strong. And also this soil gels has lots of different advantages, such as ultrafine particles. Also, you have very high specific surface area, very long triple phase boundary. We can control the homogeneity from the molecular level. Also, it's very easy to use, it's very feasible. The last part is about nano characterization. I did summarize the different methods, such as we are going to have a spectroscopy method, electron microscopy method, particularly scanning electron microscope. We call the SEM, S-E-M. Also, second one called the transmission electron microscopic method. This is called the TEM or TEM. About the scanning probe method, you can use atomic force microscope. It's called AFM. Another one is called the scanning tunneling microscope. These four methods are very commonly used to measure the morphology, the fine structures, and the elemental compositions of your different types of nanomaterials. Can be in the powder form, can be a fiber, can be a tube, can be a films, can be a three-dimensional materials. I'm going to just briefly introducing to everybody about this. Let me do the transmission electron microscope. So the transmission electron microscope, for some reason, so my figures moved. Let me go back to your scanning electron microscope. So it looks like they also moved around. So anyway, so this diagram is the scanning electron microscope, which is located in the chemistry department. So you can produce different shapes of materials. For example, this one represents a gold-coated polymer base. The goal is to produce a fully covered polymers in order to decrease the weight of these electronics and also in order to increase conductivity of the resultant materials. So how this scanning electron microscope is going to be working, let's make it very simple. So if you have the electron resources, we do call the electron gun. Under high voltage, electron beam is going to be ejected. And then you go through magnetic lenses, scanning coil, you are going to further focus on the electron beams. Your electron beams is going to be interacting with the sample. So what's going to happen? You are going to have back scattered electrons. Electron will be bounced back, called the back scattered electron. Some electrons will be absorbed by your materials, and your materials composed lots of electrons. The electrons will be scattered out, will be kicked out. You call the secondary electron, electrons. And also some electrons simply absorbed and you kick it out. And the higher energy level electrons will move back to the lower. In this case, you are going to result in emission. That emission is related to different wavelengths, particularly related to the X-ray. The wavelength is involved in the X-ray region. And then you collecting the different signals, you generate an image. That's how you are going to do it. Transmission electron microscope, so essentially similar, but you collect the transmitted electron. This slide will consider all the interactions between the electrons and your sample. First of all, your electron, here is my electron, involved interacts with your sample. The electron beam interacts with your sample. Your sample is going to absorb some of the electrons, causing the heat temperature increase. Another one is called the electron. The incident electron, incoming electron will be bounced back. You call the backscattered electron. Some of the electron can be emitted from your materials itself. You call the secondary electron. And also those electrons, they have different wavelengths. Those wavelengths is located in the X-ray region, generally speaking, so you can collect energy dispersive of X-ray. By this spectroscopy, you can analyze the different elemental composition. Some of the electron is going to be transmitted. We call this transmitted electrons. Those electrons, after transmitted, they can subject to the scattering. One is inelastic scattering, resulted in energy loss of those electrons. Another group of scattered electrons, they are elastically scattered. So this one has no energy loss. So this diagram also showed you the different electrons which moving back from the excited state to the ground state. So what's going to happen? And this diagram showed you the electron X-ray, called EDEX, X-ray energy dispersive spectroscopy. At this point, I'm going to conclude the lecture for today. You stay safe, stay healthy. Followed by, you have lots of time to learn, to understand. Enjoy.